Right, so I was curious as to how sensitive these photomultipliers out of that gas detector actually were. What I've got here, this is the multiplier assembly out of the NOx detector, which is designed to be red sensitive, and I've just put a standard 5mm red lead in the cavity there, so it's pointing towards the photomultiplier. Now, I previously tested how low a current I can actually still see the lead with my eye, and that figure came to something around half a microamp without sitting in the dark for ages. So it would probably been a bit lower if I'd have let my eye adapt to the dark conditions, but half a microamp, it was just about visible. So I've got that set up. I've got the lead going through a 1 megohm send resistor, so that will produce 1 volt per microamp. So this display is the lead current, so that's currently 0.2 microamps, so that's about half the visible level. So yeah, half the level at which I can easily see it with my eye. The second display, this is the actual output from the photomultiplier. It's just going into a 100 meg load resistor, then there's a series 10 meg resistor and a 10 nanofarad cap just to act as a filter to reduce the noise. And we've got the meter set on high impedance input. So at the level, sort of half the visible level, we're getting 8 volts out of that photomultiplier, which is clearly a very easily detectable signal. And if I just disconnect the lead and see what it goes down to, it takes a little while to settle because of that capacitor, but it does help reduce the noise, so it's a bit easier to see what's going on. And that settles down to around the sort of 30 odd millivolts level. Just check to see if any of that's actually due to ambient room lighting. Yeah, it's a very small amount. This thing's so sensitive it's actually quite difficult to get all the light. That's probably the light that's going through the blue tack that I'm using to hold the lead in place, but our sort of background dark current is about, let's call it 30 millivolts. I immediately ran out of the range on my resistance box when I was testing this, because this thing is fairly insanely sensitive. So we've got a 100 meg resistor in series with the lead, so that's clearly giving us about a 20 millivolt output, which is clearly detectable, and that's for a lead current of 7 nanoamps. And in fact, if we go put a 200 meg series resistor, we've got 4 nanoamps through the lead, and we've still got about sort of 15 millivolts above our background level. If I just turn that lead off just to double check, yep, so that's with the lead disconnected, getting towards the 30 millivolts range, and connect the lead, we've got about 15 or so millivolts for a lead current of 4 nanoamps. Right, I've connected the Peltier cooler up now. This meter is showing the resistance of the thermistor. I'm guessing by the value it's a 10k thermistor in there, so if we take a couple of amps through the cooler, we should see this going up as it gets colder. It's going to take quite a while to get to its final temperature, but hopefully we should be able to see some change in that dark current. Well, according to the manual, this thing is designed to run at about plus 10 degrees C, presumably not any lower to avoid any issues of condensation, and according to a standard thermistor table that corresponds to about 20k. So it looks like the Peltier, the temperature at the thermistor is roughly at the operating temperature. So I'll just turn the Peltier power down a bit and then just see if that stabilises. But we can see we're already down to 27 millivolts. Actually, that's even changing as I wave my hand near it. I think it must just be sort of static effects. Right, that's cooled down a bit. It has actually made a pretty substantial difference to the dark current. It's gone from 30 millivolts down to 8 millivolts, so it does actually look like it's worth doing. I've also managed to find a few more resistors, so I've now got a 1 gig ohm series resistor on the lead, so if you turn that on, that's a little over half a nanoamp of lead current. We're really getting down towards the noise now though. Disconnect that. So that, assume that's our background level, that's about 7.8 millivolts. If I connect the LED, we're getting a few millivolts, so that's still detected. So we're detecting, with it cooled, we can actually detect the output from a LED that's being driven at 500 picoamps. Now I have no idea how much light that is, but it's not a lot. Right, just for fun, I hooked up a white LED, because the white ones are quite a lot more sensitive. I found that by eye I could see that down to about 50 nanoamps. I managed to dig out some 1 gigohm resistors, so I've got 5 of these as a 5 gigohm series resistor, and I've got the bench supply, that's the top one, down to 0.9 volt, which is about the lowest. It will go and still produce some conduction through the white LED. We've still got the cooling on, so our background levels right down at sort of 0.2, sorry, about 2 millivolts. So if we now connect our LED, I've also got this meter on slow update just because I was getting so much noise. So we're now giving it about 38 picoamps through the LED, and we've got literally a factor of 10 change on the output that we're easily detecting. So yeah, the light levels on this are insanely low. You almost wonder how they even discovered those chemiluminescent reactions in the first place. They sort of seem to kick out if they need so much sensitivity to even detect them. Interesting, and that's all with the the standard voltage on the photomultiplier. I've not tweaked that up or done anything, so yeah, there's probably all sorts of optimizations you could do to get even more sensitivity. But in these things, yeah, literally any exposure of the aperture, even through sort of through a sort of convoluted path through the hole, just takes the display right off the scale. Any amount of rim light, the tiniest little crack is very, very noticeable. Right, this is the photomultiplier from the SO2 analyzer. I'm choosing this because it's a bit easier to interface to. This has got an internal buffer in it that's AC coupled, so this only produces AC signals. And again, this thing is insanely sensitive. I've got it connected up to the scope, but also to a speaker to actually hear the signal from it, which obviously a lot of that's just noise. So this has got sort of plastic cap on it, and you can get a bit of background noise, but the slightest amount of light, I mean that's the light that's sort of leaking just through this pretty much opaque plastic cap. And with all the lights out and this thing open, even like the LED that LED display from the power supply really swamps it. Just the light from the multiplex display just obliterates any signal, so this thing is just ludicrously sensitive. So what I'm going to try is actually detecting radiation. What I've got, this is the another one of these caps. This has got part of the screen from an X-ray cassette, so this should emit light if it detects radiation. But first I want to do a quick test without the scintillator just to get a baseline, because say this thing, there is quite a lot of noise, but also you do seem to get odd little noise spikes. So there are a few little occasional little spikes. Now I can only assume those are those could be things like cosmic rays, because this is an electron multiplying device. Yeah, it's fairly reasonable to assume that a beta particle could find its way and trigger the thing. So we're getting a few odd little spikes. Maybe I've run this for a while, but it averages about 4 or 5 of the bigger spikes below about here on each screenful thing. So you get a few big spikes on each scope screen. I'll now substitute the plug that's got the scintillator in it. Right, so the only difference between this plot and the last is that this has now got the scintillator in there. So this may be picking up a bit more background radiation. So We do seem to have slightly more big spikes. Obviously this is fairly random, so you'd have to do quite a lot of samples to get any statistical information, but subjectively it's sort of similar. We're getting like 4 or 5 of the sort of fairly big spikes per screenful. Now unfortunately I don't really have much that's radioactive. It's one of the few things lacking in my collections, but what I do have, these are uranium glass beads, which are very mildly radioactive. So if we stick those right on top of the detector, we do seem to be getting more. So last time we were getting an average of 4 or 5 fairly big spikes, and we're actually seeing some bigger spikes than we were seeing before. Incidentally, I have verified that an increase in light does correspond to a downward motion of the voltage, but putting that uranium glass definitely seems to have made a difference. We're getting 3 or 4 times as many spikes on the display as we were before. And I'll just take them off again to confirm. Well, that's with just the scintillator and no marble, so we're back down to the lower count level. Yeah, we do get the odd fairly big one, and say that could easily be background radiation. Right, let's try and get a bit more sensitivity out of this. I was putting a piece of scintillator straight over the hole without the plug in there, because it's daytime now. It's getting really difficult to actually exclude the ambient light, so I'm just going to use tin foil. It's about the only thing I've found that's sufficiently light proof to actually block it out, and even then the tiniest pinhole in this and it just completely swamps it. Obviously with daylight there's much more just light floating about from all directions, but about the only thing I've found that will do the job is doing this. And after being exposed to daylight it does actually take a few minutes to settle down. You can see there's still quite a lot of signal. Light, just general light sensor tends to just show itself as just noise. I think there might be some tiny pinhole in that foil. Putting another layer on just is reducing it a little bit. Yeah, I think there must have been the tiniest little pinhole in that first bit of foil. That's with another layer of foil. Just try putting those uranium glass beads on now. Detecting that quite happily now. It's got quite a bit more sensitive. That's going through 2 layers of aluminium foil, so it's only going to be picking up the more energetic particles. So it definitely is coming from those off again. Right, I just found the ideal thing for playing with this. This is a film changing bag, so it's got 2 fairly well sealed things that you can stick your hands in, so I can actually do things in front of this photomultiplier with a minimum of external light. So first thing I want to try, Triboluminescence. This is the effect where a crystalline substance like sugar cubes, if you rub them together or scratch them, they produce small amounts of light. Now see, that's very hard to see with your eyes, but I imagine this thing's not going to have any problem at all detecting this. So I only have to just barely touch these cubes together to get a response, and that's literally, they're just very gently scraping over the surface of each other. If I rub them hard, it just goes totally off the scale. That's 1 volt per division, so we've got a very substantial signal from there. If I just scrape the surface with a fingernail, even that produces quite a big signal. I'll try squeezing one just between finger and thumb. Even that's producing enough to detect quite easily, so there's very easily detecting that effect. Right, I was looking up on the net some of the other things that exhibit this. The other is sticky tape, or peeling apart pieces of sticky tape. Now there is also some stuff that came out a while ago about actually generating X-rays with sticky tape, but you do need to do that in a vacuum, so that gets a bit more difficult. So I've got the roller in here, so let's peel a bit off. Oh yes. Again, very strong signal. I think we're getting some static going on as well, because I'm sort of peeling a bit off and then we're getting a bit of an after signal, so at least some of that's probably just the static discharging. But again, very substantial signal. Right, this is one of the lenses out of that gas analyzer, and because it's designed for UV it may well be made of quartz, so I'm just going to try sort of scraping that against some glass, see if we can get any Triboluminescence from that. Yeah, and again we've got a very, scraping those together gives a very strong signal, similar to the sugar. I'm just going to try some normal glass. These are actually a couple of little LCD panels, see if that behaves any differently to the quartz. The glass produces a very small effect, but nowhere near as strong as the quartz. That's quite fun. I've actually had a few photomultipliers in my valve collection for a while. There's a huge, great RCA one. This is a tiny baby little one from I think it's from some sort of film scanner or something. It came as a board with 3 of these. There's another Hamamatsu one. I just peeled the coating off to see inside it, but there's some graphite shielding on the outside so you can't see. But no, just amazingly sensitive. Not obviously they've got very sort of niche uses. I suppose it might be interesting to make some sort of image scanning thing to work as a low light camera, but the obviously the scanning process, you'd have to scan quite slowly, because although the devices themselves are quite fast, because of the very high impedance, the capacitance is going to limit the bandwidth you can get through. But I suppose you could have make some sort of either mirror scanner thing or something that scans a dark scene with a very low light flying spot. But I somewhat doubt I'm going to have time to play around with that. These photomultipliers will probably end up on eBay, because I can't really think of much else that I want to do with them. But yeah, interesting bit of very old tech, but still probably about one of the most sensitive light detectors you can get even today.